Okay, this is the Moore's circle example from section 17.8. A long metal block 4x4 in cross section is subjected to a compressive load of 32,000 pounds. Using Moore's circle, A determine the normal tensile and compressive stresses and shear stresses on a plane that is inclined 60 degrees counterclockwise from the x-axis, as shown, and determine the magnitude and maximum shear stress and location of the plane at which it acts. Okay, so here's our solution. First of all, we have to find what the maximum compressive stress is. So our sigma y equals negative p over a, just 2,000 psi compression. The radius of the Moore's circle, in this case, since there's no forces in the x direction, equals 1,000 psi, p over 2a. So here's our Moore's circle right here. Our maximum stress is this sigma y right here, which is 2,000 psi negative. Notice that this is the shear stress axis. We are to the left of the shear stress axis, so our that's because our sigma is tension. And then we notice our sigma in the x direction is 0, so that's why this Moore's circle here is now tangent to the y-axis, because sigma x equals 0. To find the normal and shear stresses at 60 degrees, we need to understand that the Moore's circle internal angles represent 2 theta, which kind of makes sense when you look at this, because we always said that shear stresses are its maximum, 45 degrees. This plane angle would be 45 degrees to give us our maximum shear stresses. We learned that in section 11. And then put in the Moore's circle, that's 90 degrees. Okay, so the maximum shear stress at 90 degrees is actually at 45 degrees in terms of rotating this plane. So one thing you got to remember about the Moore's circle is that the internal angles are always at 2 theta. Okay, draw the circle radius at 120 degrees from M to D. Okay, so from drawing a line from M to D at 120 degrees. Okay, so this represents, this point D here represents what our shear and what our normal forces are going to be at that point. Okay, so the value on the y-axis is going to be our shear stress, and then the value on the x-axis, where it intersects with point C, that is going to be our normal stresses. So the y value of point D is the shear stress, the x value of point C is the normal stress, and then we're going to use a similar 60-degree triangle to solve. Okay, so we're going to use our trigonometric functions. So tau, our maximum shear stress, equals r sine of 60. That's just looking at this triangle right here. R sine of 60 gives us this 866, which is our tau. And then what our sigma is going to be is, I'm going from 0 to m, which is negative 1,000, and then using this triangle right here, negative 1,000 cosine 60 is 1,500 psi. So negative 1,500 psi. So these are our shear stress at 60 degrees and our normal stress at 60 degrees. And then when we do that, we're going to be drawing this rotated element. Okay, so we're going to draw this rotated element. We're going to draw it at this 60 degrees here, and then we know our shear stress is going to be 866 psi, and then we also know that our compressive stress, our normal stresses are compressive, and they're 1,500 psi. So that is how to understand Moore's circle for example problem 17.9. And then I'm going to be talking about an example problem 1710 next. but I'm going to do that in a separate video.